In a landscape where the future of electric transportation appeared irrevocably tied to a handful of costly minerals, a recent declaration from Tesla has sent destabilizing tremors throughout the automotive sector. The industry is now abuzz, dissecting the latest strategic maneuver from Elon Musk. Central to this upheaval is Tesla's introduction of a novel electric motor, an innovation framed not as a mere incremental upgrade, but as a foundational shift poised to redefine established paradigms. This motor is engineered without the use of rare earth elements, thereby severing a dependency that has underpinned virtually every electric vehicle manufacturer until this point. Where reliance on these materials has historically driven up costs and strained global supply networks, Tesla claims to have eradicated this vulnerability entirely. More astonishingly, initial reports suggest this rare earth-free design achieves superior power, efficiency, and overall effectiveness compared to traditional counterparts, representing a paradoxical advance in performance through subtraction. The core of this breakthrough lies in a fundamental reimagining of magnetic technology. By refining the electromagnetic interplay within the motor, Tesla asserts it has significantly boosted vehicle range while markedly reducing energy waste. The practical implication for consumers is a reduction in charging frequency, greater travel distance per charge, and lower operational expenses. This development has sent rival manufacturers, from industry titans like BYD to factions within Tesla's own ranks, into a frenzy of analysis. A critical question now emerges: is this primarily an environmentally motivated gambit, or does it conceal a broader tactical play to consolidate dominance within the electric vehicle market? The potential for this motor to recalibrate the fundamental dynamics of cost, technological progression, and competitive standing in the automotive industry is profound. It was against this entrenched backdrop that Tesla's announcement landed like a seismic shock, rattling the entire ecosystem. The notion of a high-performance electric motor completely devoid of rare earth elements was long considered a practical impossibility within engineering circles. Upon its revelation, disbelief quickly gave way to widespread astonishment. Engineers were perplexed, investors recalibrated their positions, and competing automakers were left to ponder the veracity and implications of a claim that threatened to rewrite the industry's rulebook. To appreciate the innovation, one must first understand the basic principle of electric motor operation, which centers on the interaction between magnetism and electrical current. Electricity flowing through coils generates a magnetic field, which in turn produces rotational force to drive the wheels. Traditionally, maximizing this power has relied on integrating potent permanent magnets crafted from rare earth metals. While effective, these magnets are expensive, add substantial weight, present thermal management challenges, and perpetuate strategic supply dependencies. Tesla's approach originated from a fundamentally different question. Instead of seeking superior magnets, the company investigated whether such deep magnet reliance was necessary at all. This line of inquiry led to a radical redesign of the motor's core electromagnetic system. In essence, Tesla engineered a more intelligent dialogue between the magnetic fields and the electrical currents. Power is no longer derived predominantly from the intrinsic strength of heavy permanent magnets, but from precisely orchestrated control, manipulating the timing, intensity, and shape of the magnetic field itself. A useful analogy is the difference between relying solely on a heavier hammer for more force versus achieving greater results through refined technique and precise application of energy. Tesla's new motor dynamically modulates the magnetic field, delivering force exactly when and where needed, rather than maintaining a constant, wasteful output. This control-centric methodology allows the motor to match or exceed traditional performance without rare earth elements, as the efficacy now stems from software and system design, rather than from the material composition alone. This intelligent use of electricity also generates less waste heat, enhancing motor longevity, ensuring stable performance, and reducing maintenance intervals. Furthermore, eliminating heavy rare earth components reduces the motor's overall weight. A lighter propulsion system means the vehicle expends less energy moving itself, directly extending the operational range from an identical battery pack. This addresses a primary consumer concern and expands the practical utility of EVs beyond urban confines. An additional, often overlooked benefit is performance stability over time. Rare earth magnets can gradually degrade, particularly under thermal stress, whereas the new design promises more consistent output throughout the vehicle's lifespan. This technological pivot has the potential to transform the competitive landscape, shifting the focus from a contest over mineral access to a battle of ingenuity, control software, and systemic design. This evolution brings us directly to the paramount consideration for consumers and manufacturers alike: real-world performance. The ultimate metrics of success for any EV are its range, acceleration, and durability. Tesla's new motor purportedly redefines these parameters not merely by increasing raw power, but by drastically improving the efficiency of its application. A historic limitation of electric motors has been thermal losses. As power output climbs, so does heat generation, which siphons energy away from propulsion and can lead to performance throttling. The new motor's precise, on-demand power delivery mitigates this issue. By avoiding constant peak output, it reduces unnecessary stress and thermal buildup. The conserved energy is then available for extending range or maintaining speed, making performance more sustainable. This also results in smoother power delivery, eliminating jerky acceleration and providing a more refined driving experience that concurrently reduces wear on mechanical components. Critically, this motor is said to maintain its power band more effectively at higher speeds, addressing a common experience of fading acceleration in older EV designs. The reduction in thermal load lessens the burden on cooling systems, further contributing to weight savings and efficiency gains. From a longevity perspective, lower operational temperatures help preserve the motor's internal components, suggesting that the vehicle's driving character and capability could remain consistent for many years. In simpler terms, this motor achieves high performance without the associated fatigue, offering reliability alongside power. This holistic advancement means that high performance may no longer be the exclusive domain of luxury-priced vehicles, as efficiency and power become more economically achievable. Tesla's breakthrough, therefore, is not just about more potent hardware, but about a smarter, more sustainable approach to performance that could reshape market expectations. For the everyday driver, these technical transitions translate into two tangible, life-altering benefits: significantly reduced range anxiety and lower overall costs. The efficient use of electricity means more miles can be extracted from each kilowatt-hour stored in the battery. This diminishes the constant need to seek charging stations, making daily commutes, school runs, and weekend trips far more convenient and spontaneous. The psychological burden of meticulous range calculation begins to fade, fostering a get-in-and-go mentality akin to that of conventional petrol vehicles. This ease of use is a critical prerequisite for mass consumer adoption. Concurrently, the removal of expensive rare earth metals from the motor's bill of materials directly attacks a major cost driver in EV manufacturing. Freed from the price volatility and geopolitical constraints of these materials, production costs can stabilize and decrease. These savings can potentially be passed to consumers, bringing purchase prices closer to parity with internal combustion vehicles. When combined with already low maintenance costs, electric vehicles shift from being a premium or ecological choice to a pragmatically superior one for a vastly larger segment of the population. Looking toward the horizon 5 to 10 years hence, the automotive world will be unrecognizable. The dominant question will no longer be whether to buy an electric car, but which electric car to buy. Charging infrastructure will achieve ubiquity, vehicles will be lighter, smarter, and more dependable, and prices will continue to fall as technologies like the new motor mature and proliferate. Electric mobility will transcend urban centers and affluent demographics, reaching into small towns and rural communities globally. The narrative will evolve from environmental sacrifice to one of superior convenience, performance, and economy. Moreover, the industry will expand beyond traditional automotive boundaries, becoming an integrated nexus of software, energy storage, grid management, and data services. The enterprises that thrive will be those that master this complex, interconnected ecosystem. Tesla's latest announcement is far more than a product update. It is a catalyst poised to trigger the next and perhaps most decisive phase of the electric vehicle revolution.